Okay, our last day of this unit is going to be working with similarity in right triangles. So in these ones, we're going to start out with one great big right triangle and see what happens when we draw an altitude in it. Now see, I've got this big right triangle here, this blue one. It's a right triangle. If I draw an altitude down from this right angle vertex to the hypotenuse, it's perpendicular because it's an altitude. And it creates a right triangle here on the left, and it creates a right triangle here on the right. And the thing that we have proven, that we're just telling you now, is that in a right triangle, when you draw an altitude, it creates three similar right triangles. Okay. And here on the right they all are. And these make all sorts of fancy proportions that you can memorize. In this one to the right here, it says the ratio of the short leg. And so if you look in the picture, the short leg looks kind of like BC. So BC, okay, to the altitude, so the altitude is BD, that fraction is going to equal the hypotenuse of the whole thing, so AC, and the longer leg, which is this leg up here. And some people memorize that, and they get really good at it. And if you can memorize this, that the short to the altitude is the same as the hypotenuse to the longer leg, you can learn that. Because look, this short guy over here is a hypotenuse of the green triangle, okay? And the altitude is the longer part of that triangle. So you're really doing hypotenuse to altitude, okay? And then you're doing hypotenuse and longer leg. Hypotenuse and longer leg, hypotenuse and longer leg. Some people can remember this. If you cannot remember this, you don't have to memorize it. Instead, I'm going to show you how you can just figure it out and set it up every time. Because remember, corresponding parts in similar triangles should make proportions. They should make equal ratios. And so if you know what parts you have, you can make those ratios without having to memorize this every time. So coming here, I'm going to take this big blue right triangle and figure out all the similar corresponding stuff. And so if I look at it, I'm just going to eyeball it, and I'm going to say, you know what, RQ looks like the shorter of the legs, and PQ looks like the longer leg. And this is my hypotenuse because it's a cross. And using that, once I cut my altitude from the right angle to the hypotenuse, I'm going to create this red right triangle over here. And the thing you need to remember is that the short leg on my blue triangle is next to the short piece of the hypotenuse. See how my hypotenuse got cut into two pieces? And the short leg is next to the short piece. And the long leg will be next to the long piece. But wait, there's more. Because that short piece of the hypotenuse will be the short leg of my smaller right triangle. And so this is the short leg. This would be the longer leg of my red right triangle. And then this is the hypotenuse of my red right triangle, because it's across from that right angle. So short leg of the big guy is right next to the short leg of the little guy. Over here, the long leg of my blue triangle will be next to the long piece of the hypotenuse. And the long piece of the hypotenuse is going to be the longer leg of this little triangle down here. And the altitude is now the short leg of that triangle, and PQ down here is your hypotenuse. And so having that set up, you can then identify the similar triangles. So let's start with the blue one. The blue one, I'm going to call him PQR. Let's just be in alphabetical order. So PQR. When I go from P to Q to R, I'm going down the long leg to the right angle and then up the short leg. When I go to do that with the red one, let's see which one's the long leg. Well, this was the short leg of my big guy. This will be the short piece of my red one. So this is the long piece. And I want to go toward the right angle. So Q to S, and then across to the R. So I'm matching pieces up. For the green one, remember when I went from P to Q on the blue triangle, I was going down the long leg toward my right angle. When I'm looking at my green triangle, if I want to go down its long leg toward the right angle, it's going to go from P to S. So I'm going to go from P to S, and then down the other side to Q. So those are your three similar triangles. If you can keep track of short, short, and long, long, you can figure out which ones they are without having to try to memorize that the short leg to the altitude is proportional to the hypotenuse in the long leg. Because I can't ever remember that. I end up just using the similar triangles to keep it straight. Now if I want to draw them in the same orientation, let's draw them. So here's my blue one, and its right angle is over here, and I've got P, and then Q, and then R. And Q is my right angle. If I want them to have the same orientation, then I would want to draw my red triangle with its right angle over here. Well, the right angle on my red guy is S. Okay? And now its corresponding bottom piece has to be the one that corresponds to PQ. PQ is the long leg of my blue triangle, so the long leg of my red triangle must be this one, must be the altitude, because the short leg of the blue guy went with the short leg. Okay? So my long leg will be QS, and my short leg will be SR. So I have long and short here, and now I have the long one and the short one here. Then when I go to the green guy and draw him, remember I'm going to want the long one and the short one oriented in the same way. Well, the right angle of my green triangle is at S again, and the long side is here on the bottom. Well, the long side of my green triangle is PS, so I'm going to put it that way. And then the short side is SQ, so there's SQ. You could also use the letters in here to help you orient them if you want. Okay? So short leg, short piece, short leg of the little triangle. Long leg, long piece, long leg of the littler triangle. Using that, you can either have this memorized up here and use it to find missing numbers, or you can use what you know about the similarity to find your missing numbers. So in this triangle, they want me to find the altitude. And I could remember that the ratio of the short leg to the altitude equals the ratio of the hypotenuse to the long leg. I could do that. So I could say the short leg, 9, to the altitude, x, is proportional to the ratio of the hypotenuse, 15, to the longer leg, 12. I could set that up. But I might not remember that. And so if I didn't have that memorized, I could look in here and go, well, this is a short leg, and this is a long leg, because 9 is smaller than 12. And this is my hypotenuse. And I could say, well, my short leg goes with the short piece, and the long leg goes with the long piece. And then I could focus on one of these little triangles to set up. And I could say, well, let's see. In my red triangle here, x is being the short leg, because the long one's over here and the 12 is your hypotenuse. So I could say x is my short leg, and its across from, and its width my hypotenuse 12. And since I did short with hypotenuse, then in my blue triangle, I could say, well, the short part of my blue triangle here is 9, and its hypotenuse is 15. And I could set it up that way as well. So there are 8 correct ways to set any of these proportions up. You can do it by memorizing this relationship, or you can look for the similar parts in the triangle. Either way, when I cross multiply, I end up doing 15 times x. And either way, when I cross multiply, I end up doing 9 times 12, and that's going to be 108. And so x ends up equaling 7.2. So again, you can memorize short leg to altitude and hypotenuse to long leg, or you can set up similar triangles and remember which piece goes with which. In this example, I've got the 3 legs of the triangle, and I'm just trying to find my altitude. Okay? I can memorize that short leg, this is my short guy up here, goes to altitude, so 11.2 goes to x, and then the ratio of the hypotenuse to the longer leg. So my hypotenuse is 23.8 and 21. I could memorize that, or you can look for corresponding parts of similar triangles to set it up. When you set this one up, you get 23.8 going with x, and 21 times 11.2 is 235.2. And when you solve it, x ends up being, rounded it to 9.88. Excuse me. And so, memorize or set up. Over here, I'm trying to find the altitude, and I know that the short leg, over here, 7 is shorter than 24, so short leg with altitude is going to equal hypotenuse with long leg. And so you have 25x equaling 168, and x comes out to be 6.72. Again, if you don't memorize this relationship, you can set it up. I'm going to set this one up again just for giggles. I can ignore what I remembered up here and just say, oh, this is my longer leg of my triangle, so this will be the long piece of this little guy down here. And I don't know how long it is, but if this is the long piece of the blue triangle, x will be the short guy. And so if I do x being short and 24 being the hypotenuse, then when I go back to the big red triangle, my short guy will be 7 and my hypotenuse will be 25. And I still end up doing 25 times x, and I still end up doing 24 times 7. So either way will get you the same result. Okay? Now, we're going to diverge a little bit, and I'm going to show you something else a little different, because we're going to use, this will be another time where you can either memorize this or use similar triangles. And what I'm offering you to memorize is something called mean. Now, back in the dark ages of elementary school, you learned something called arithmetic mean. It looks like arithmetic, but it said arithmetic. Arithmetic mean is what you do when you add things up and then you divide. And you probably called that averaging, okay? Add stuff up and divide. We're not going to do arithmetic mean here. We're going to do something called geometric mean. And with geometric mean, instead of adding and dividing, we are going to multiply and square root. So the geometric mean of 2 numbers, so let's call them A and B. If I have 2 numbers and I want to find their geometric mean, what I would do is I would multiply those 2 numbers together and then square root them. That's it. That's all it is. Instead of adding and dividing, that's arithmetic mean, we're going to multiply and square root. And so if I want the geometric mean of A and B, I I multiply and square root. So if I want the geometric mean of 6 and 30, I'm going to do 6 times 30 and then square root it. Well, the square root of 6 times 30 is, I'm going to give that an x, that's going to be the square root of 180, and now you're going to have to simplify that. Well, that's 36 times 5. 36 is a perfect square, 5 is not. And so the 36 square roots to be 6, and the 5 stays underneath it. This is called the geometric mean of those numbers. It's not the same as the average you learned back when you were a little kid. This is a big kid geometric mean. Okay? The geometric mean of 16 and 28, that means to multiply them and square root them. Okay? And that's going to give me the square root of 448. And you can break that down lots and lots of different ways. It just so happens that this is 64 times 7. And 64 is a perfect square. So when you square root 64, that gives you an 8, and then the 7 stays underneath. This is your geometric mean of the pair of numbers. The geometric mean of 12 and 50, instead of adding and dividing, we're going to multiply and root. So we're going to do 12 times 50, and then we're going to root it. So that's going to give us the square root of 600. Well, 600 is 100 times 6, and 100 is a perfect square. So when I square root it, I get 10, and the 6 stays underneath. That's geometric mean. The reason we learned this, and the reason I'm telling you this, is first, now you know a fancy math word. But now I'm going to take this and go, well, if I wanted the radical off of here, I could square both sides and know that if I square my geometric mean, it gets me back to whatever the two numbers multiplied was. Why do we care about this? The reason why we care about this is what you would get if you had a proportion that's got the same number on the top of one fraction and the bottom of another. If I had this proportion and I do the cross product to solve for x, I end up getting x squared equals ab, which means that x, this little number that's in two places, is the geometric mean of the other two guys. And we've been doing lots of proportions. And so anytime you do a proportion that's got the same guy on top and bottom, you can say that that number that's on the top and the bottom that's the same is the geometric mean of the other two numbers in your proportion. And it's just a neat fact to know. We use that sometimes in statistics for lots of other stuff, but for now you just get to learn the fancy math word. So when we turn it over and use that, it turns out that that happens in these right triangles that have an altitude in them. Okay? So if I have an altitude in a right triangle, that altitude is the geometric mean of the two parts of the hypotenuse. Okay? And so how do I get the geometric mean of those two parts? Well, I take them and multiply them. So AD gets times by DC, and after you multiply, you root them. So the altitude is the geometric mean of the two segments of the hypotenuse. Okay? And that happens naturally if you want to set up these similar triangles that we learned before. So if you can't remember that the altitude is the geometric mean of those two pieces of the hypotenuse, it's okay. It'll still work out if you set it up. Let's do this first one both ways. Oh look, I have a right triangle. Its hypotenuse is cut into two parts by the altitude. And I want to know how big the altitude is. Well, one way I could do this is remember that that altitude is the geometric mean of these two pieces of the hypotenuse. And so to get that geometric mean, I'll multiply them and square root them. So I would know that x is equal to the square root of 96, which breaks down into 16 and 6. Oh look, 16 is a perfect square. So the square root of 16 is 4, and the 6 stays underneath. That's one way you could set it up. But what if you're on the test and you panic? And you're like, I can't remember which thing is the geometric mean and which ones you use to do it. If you're stuck, you can still come in here and say, oh look, here's my two parts of the hypotenuse. This is the shorter piece, and this is the longer piece. Well, remember the short piece here goes with the short leg of the whole triangle. And the long leg of this guy goes with the long leg of my big triangle. And now I could set up any proportion I want. So let's say I did it with this green piece, and I want x to go with 8. Well, let's see, x is, well, 8 is the short piece of the green triangle, and this is the hypotenuse of the green triangle. See how it's across from the right angle? So x must be my long leg. And then, when I look in the whole big triangle, the whole big blue guy, okay, oh, I didn't know my short guy on the big one. So I'm not going to use my short piece. Instead, the only thing I know in my big blue triangle is my hypotenuse. And so I would go, okay, so my hypotenuse, oh, I can't use that either. I'm going to use I'm sorry, whoever is listening to this, I'm going to do my little green triangle and set it up with my little red triangle. I don't have enough of the big blue triangle. I only have its hypotenuse, so I can't use it at all. But I have 2 pieces of the red guy, and I have 2 pieces of the green guy. So that's what I'm going to use. So in my green guy, I've got x and 8. And in my red guy, I've got x and 12. So let's see, I'm going to have long going with 8, which is my short piece. And then in my red triangle, which one is the long one here? Oh, it's the 12 is the long piece, and x is the short piece. Okay, because here's the long. See, we wrote long. And so x must be the short piece. And look, when I cross multiply that, I get x squared equals 8 times 12, which is 96. And when I square root it, I'm back here. Now, I probably confused you with that because I got lost halfway through. So let's try a new one. We'll do it the long way first and then the fast way. So on this one, I have my whole hypotenuse is 37. I've got the little piece is 5. And so this part down here, this orange feller here, if I take 37 minus 5, that gives me 32 for the other part. And I'm trying to find the altitude. Now if I do this the long way, I'm going to use my 2 triangles to figure this out. So I'm going to use my little green guy and my orange guy. If I use the orange and green guys, 5 is short and 32 is long. So if 32 is the long guy in my orange, x is the short piece. So if I set up short over long in my orange triangle, short would be x and long would be 32. Now I come over here to the green triangle. Short is the 5 guy. And so long must be x. And so I could cross multiply that, and x squared would equal 160, and x would be the square root of 160, which is going to be, let's see, that's 16 times 10, so 4 root 10. That's a long way you can do that. If you want to take the shortcut, you can just say, oh, x is the altitude, and the altitude is the geometric mean of the 2 parts of the hypotenuse. So it'd be the geometric mean of 5 times 32, which is going to put you right back here. So you can use either method that you like. Okay. Down here, this time I have the altitude. And so you say, okay, I know that my altitude is the geometric mean of these two pieces. So it's going to be whatever you get when you multiply the two pieces and then square root. So to work this out, how do I get rid of the radical? I'm going to square it. But if I square the right, I got to square the left. And so that's going to give me 324, and the square root and the square cancel out, equaling 15x. And when you divide it off, x equals 21.6. If you can't remember this relationship, again, you could set up and say, okay, what do I have going on here and what parts go where? Okay? And in this triangle, you could say, oh, look, this is long and this is short out of just this little right-hand triangle. If this is longer and this is shorter, then this is the short piece of the hypotenuse and this is the long piece of the hypotenuse. And you can go from there to set up your proportions using the similar triangles. Over here, I have the altitude, and they're wanting the whole hypotenuse. And so what I'm going to do is I'm going to say, I don't know this little piece. I'm going to call him y. And I'm going to use this relationship I know that works with the leg, sorry, not the leg, the pieces of the hypotenuse. I know that the altitude has to equal the geometric mean of these two pieces of my hypotenuse. And so when I solve this by squaring it, 441 is going to equal 30y. And so this little piece I didn't know is going to be about 14.7-ish. Okay? But that's not what I was wanting. I was wanting x, which is the whole hypotenuse here. So x, I'm going to have to do 30 plus that 14.7, which comes out to be 44.7. And again, if you cannot remember this geometric mean rule, set up your proportions using similars and say, okay, in my little purple triangle here, this is short and this is long. If this is the long piece of the hypotenuse, this is the short piece of the hypotenuse. And this is the long side of the big triangle, and this is the short side of the big triangle. And you can still set up all your proportions that way. Okay? Another theorem we have has to do with the legs in geometric mean. Okay? For this one, it says the length of the leg of the triangle. So here's my big triangle. The length of the leg of the triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse adjacent to the leg. So what you're going to do is you're going to pick one of your legs. Let's say I picked AB. Okay? That leg is the geometric mean. So AB is the geometric mean of the hypotenuse, AC, and the piece of the hypotenuse that's next to my leg. Well, since I picked AB, it would go with AD. And you could set that up. But what if I wanted to play with this leg of the triangle? The length of this leg of the triangle, so BC, is the geometric mean of, again, the whole hypotenuse and this little piece of the hypotenuse. So again, we're playing around with the chunks of hypotenuse. And you've got these guys. Now, again, if you can't remember this shortcut rule, you can use your proportional similar triangles and just set up short with long, however you want to do it. Okay? But this is a shortcut you can use where you can memorize that one of the legs is the mean of the whole hypotenuse and its chunk. Okay? So here, I want one of the legs. Well, I know it's going to be the geometric mean of the whole hypotenuse. Oh, I don't know the whole hypotenuse. But I can get it by doing 24 plus 2 and getting 26. So my leg will be the geometric mean of this hypotenuse and the chunk here that is next to the leg I'm focused on. When I do that, x squared is going to equal, sorry, I shouldn't have squared that yet. X is going to equal the square root of 624. And when you break that down, it just so happens to be 16 and 39. Convenient that it had a perfect square. So x is going to equal 4 root 39. Could you have set up this similar right triangles and used, oh, this is the short piece and this is the long piece, so this is the long leg of the big guy? Yes, you could. Or you can memorize this theorem. Trying another one. I'm looking for a leg of the triangle. I know that the leg is the geometric mean of my whole hypotenuse. And, oh, I need this chunk that's right next to the leg. I don't know it, but I know I can find it by doing the whole hypotenuse minus 7, and that's going to give me 5. So my leg will be the geometric mean of the whole hypotenuse times my neighboring chunk. So x is going to equal the square root of 60. That breaks down into 4 and 15. 4 is a perfect square, so x is 2 root 15. Okay. Coming down here then, we're wanting to do that with this guy. I know that z would be the geometric mean of my whole hypotenuse in this chunk, but I don't know either of those. I don't know the chunk, and I don't know the whole hypotenuse. So you can start looking down at other right triangles and realize that, oh look, over here the altitude makes a right triangle here. And I can use these two sides to find the third one using the Pythagorean theorem. I know how to do that. And so I can say a squared plus b squared equals c squared. Y squared plus 24 squared equals 27 squared. And so y squared plus 576 is 729. And y squared, when I subtract, ends up being 153. And when I square root both sides, y ends up being the square root of 153. And 153 breaks down into 9 and 17. So it's going to be 3 root 17. Or you could round it to about 12.4. So now you've got 12.4 there. That gave me my y. Well, now I want to set up something I can find something else with. Well, this is my altitude. 12.4 was my altitude. And remember, your altitude has one of your special relationships. It's the geometric mean of my two chunks. And so I could say my altitude, 12.4, is the geometric mean of my two chunks of my hypotenuse. One chunk is 24. I don't know this other chunk. I'm going to call him A. And so when I do that, I can solve this by squaring both sides. And let's see, 12.4 squared is going to come out to be 153.76 equaling 24 times A. And when I divide by 24, A ends up being about 6.41. So this little chunk is 6.41. And so you go, oh, round it to the nearest tenth. I'm sorry, I was supposed to round to the nearest tenth, and I put a nearest hundredth. I am ashamed. I am ashamed. I was only supposed to do to the nearest tenth. So now I've got that piece. Well, now that I've got this is 6.4, I can use the 6.4 with the 24 to find out that this whole distance, adding them up, is 30.4. So that's my x. Here's my y. Now that I've got that, I can use this leg relationship to find z. I can say that z is the geometric mean of my whole hypotenuse and the chunk right next to it. And so z is going to equal the square root of whatever all this garbage is. I believe it comes out to be 194.6. And so Z is approximately 13.9. So we had to use both of these relationships and the Pythagorean theorem to find all the different stuff. And it's going to be on you as you work through these to figure out which one you can use. Or you can always go back to, I've got short and long and short and long, and just go with it that way and set up the proportions based on where things are in the triangle. On this last guy, I've got two pieces of this purple right triangle, so I can do 8 squared plus 20 squared, and that's going to give me my y. And so when I work that out, y ends up equaling about 21.5. And that's one of the pieces I want. All right. Well, then I can go, okay, well, what else can I do? How can I find something else here? Well, I know that my altitude right here is the geometric mean of the two chunks. So 8 will be the geometric mean of 20 and x. And so, okay, so 8 squared, so if I square both sides, I'm just going to write that down that way. If I square both sides, that gives me 64 is equal to 20x. And then when I divide off the 20, x is about 3.2. So that's about 3.2. Which means my whole hypotenuse now is going to come out to be 23.2 from end to end by adding up those two pieces. Now I can use one of my rules or Pythagorean theorem. So I could either use my short leg is the geometric mean of the hypotenuse and the chunk, or I could use the Pythagorean theorem with the 21.5 and the 23.2. I'm going to use Pythagorean theorem. So z squared, well, I could either do z squared plus 21.5 squared equals 23.2 squared, or I could do the geometric mean rule where I do z squared is equal to, so this leg is the geometric mean of the hypotenuse and the chunk. Either one of those, either the Pythagorean theorem or my leg theorem, should get me z being about 8.6. Okay? So you have lots of options solving. You can memorize that the altitude is the geometric mean of the two chunks, and you can memorize that the leg is the geometric mean of the hypotenuse and your next door neighbor chunk, or you can just go back and use your similar triangles to set up your proportions.